if you would have asked me a few years ago, would politicians ever want to show up at wafer fabs and get their picture taken? I'd have thought you were nuts, you know. But now
Yeah.
they come from everywhere.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. There aren't many US-owned companies that can make you a chip. Like a computer chip, not a potato chip. In fact, there's just one company that specializes in this, SkyWater Technology. We're joined today by Steve Kozer, the CTO of SkyWater Technologies, to explore the state of fabs in 2022 and why rushing to the next semiconductor technology node isn't always the right decision for a fab, especially if you need to solve creative IC architecture challenges. Steve, I love geeking out on semiconductors, so I'm really excited. Thanks for chatting with us today.
Well, I'm excited to do it.
So how did you get into tech? Is it something you always knew you wanted to do?
Well, no, Daniel, actually not. If I think back to how I got involved in technology, it was really much more, practical than that. I grew up in South Dakota and needed to get, money to go to school. And I learned that you could get a ROTC scholarship if you said you were going to be an engineer and you had grades that were good enough. So, my scores were good, my grades were good. I applied, so I went and joined University of Minnesota Army ROTC program as an engineer. So that's how I became in the engineering field. So it's not because I was always dreaming of being an engineer or anything like that. I didn't know any engineers. I don't know if there are any, where I grew up. So that's how I got into engineering.
And then why electrical?
Well, honestly, electrical it's just because that's what they said they wanted the most of, and that improved your odds of getting the scholarship.
Well, that's a pretty good reason. And then you were in ROTC?
So I was in Army ROTC for a year. That didn't really agree with me so well, but I stuck with engineering because I did like that. But that's how I got in.
Okay. Yeah, clearly you stuck with it because you got advanced degrees as well. Can you tell me what you studied and researched?
Right. So I went to the University of Minnesota in Twin Cities and got a degree in electrical engineering. And then what I specialized in at Minnesota was semiconductor manufacturing program, which at that time was a certificate. And it just meant that you took some classes in semiconductors and device physics and circuit design. And, there was a lab course also that you could take. And so I was interested in that. And then after graduating, wanted to go to grad school and study in the area further. There was a lot of interesting things that seemed like could be done, but you needed an advanced degree to really do those things. So I applied to grad school and was had the good fortune to be accepted at University of Arizona and join a group that was doing device physics kind of work in the radiation effects space. So yeah, that's how I got there.
What was it like coming out of high school with very little perception of what an engineer is and does, and then jumping into an engineering program?
Well, I got to admit, it was a bit of a shock. And I wasn't really all that prepared. And, it's kind of a classic story of a kid that, shows up in the big city. And the key is how quickly can you realize that you don't really know as much as you think you do. So for me, it took a little longer than I would have liked, but I eventually did figure it out. It's probably much less so today with AP classes and all the online tutorials and so on that you can take to get prepared. But back in the day, of course, I'm dating myself, but back then, the only thing that you knew is what you learned from your teachers in school and studied. And so there's quite a bit of geographic disparity, let's say, between what you might learn in the Twin Cities metro area versus what you might learn in South Dakota.
I had a very similar experience. I came in with little to no calculus or physics, zero coding,
Yeah.
and jumped into a program. And I was also kind of the pre-YouTube era of high school. And
Right.
it was quite a shock. So I'm impressed that you were able to leverage that and get with the program, I guess.
Well, yeah. And, because you're dealing with kids that really they'd already taken calculus and physics. They were just retaking it. It wasn't really necessary for them to listen to the lectures and stuff. So I was in a different place, but eventually figured it out and got through it. So that was a good experience.
And then you moved into semiconductors and device physics. How did that happen? Was that part of a program and part of your studies?
Well, what it really was is that a part of the required course curriculum for electrical engineers at the time was that you needed to take one class in transistor physics, device physics. So, how does a MOSFET work? How does a BJT work? And that was a prerequisite to take analog design 1 and 2. So it was really in that class that I found that I was interested in that kind of stuff, and it was taught by Ray Warner, who's passed away now, but he was a great teacher and a great presenter of that material, and I just loved the way that the fundamental equations combined and made structures that were so incredibly useful, and how that all fit together. It was really it was the required junior level device physics class that really got me interested in that area. And I'm emphasizing required because most colleges these days don't require it anymore, and they just kind of skip it. It's maybe a senior elective or something, but back then it was required. So that's why I was exposed to it. So that's how I really got interested in it.
Fascinating.
Yeah.
And then I'm told that 5 of your research papers have reached seminal status. Can you tell me what that means and maybe what a couple of those papers were about?
Right, right. So fast forward to Arizona and doing work in the radiation effects lab there. Under my advisor was Ron Schrimpf, and great advisor. Also, coincidentally, a student of Ray Warner's at Minnesota. So there's a connection there, kind of a lineage. So the research group was working on lots of different things, all related to radiation effects on microelectronics. And the basic thing is that it's a reliability physics kind of problem where radiation causes damage of various kinds. Transistors are affected in various ways. None of these ways are good, and you want to understand why is it happening, how do you prevent it, how do you understand it, what's really going on, behind the scenes. So anyway, so one of the big problems at the time in the community was the fact that you could, for bipolar transistors, BJTs, it was observed that sometimes you would irradiate the samples at a low dose rate, and they would actually degrade more than if you irradiated them at a high dose rate to an equivalent level of dose.
Weird.
So that's counterintuitive. You would like to think that no matter how fast you irradiated something, if you got to the same total dose of radiation, the response would be the same. But that wasn't the case. And people didn't really understand why that was. It didn't make sense.
So why is that the case?
It turns out that the reason has to do with Shockley-Reed-Hall recombination in a depletion region under forward bias conditions. And the trap charge can influence the shape of that, broaden the Shockley-Reed-Hall recombination peak, and give you an apparent increase in excess base current leading to beta degradation. Anyway, all of that was not really understood, and it was not really well understood how trapped fixed charge in an oxide could be causing degradation in a forward bias p-n junction beneath it in a clear way. So anyway, we were able to do experiments that teased out these things, simulations, and so on. That basically what it goes by today is ELDRs, or enhanced low dose rate response. So
Okay.
it's an important practical problem because you want to irradiate things quickly and get an answer fast. But
Hmm.
if the physics is different depending on how fast you irradiate, then you have to really understand why. So actually, I went and looked at it since we brought this up. So what does seminal status mean? I don't know. People have different definitions. In this case, 100 or more citations on Google Scholar in this field is about seminal. So actually, it's not 5. There's only 3 seminal papers.
So heavily cited is basically, which generally implies people are building off of your work.
Exactly. So people keep doing more and more and more work in the field of enhanced low dose rate response.
Is that like a space type situation where, satellites, aerospace defense, is the low dose rate more consistent with what it experiences in the real world? Or what's the value of researching that?
Yeah, right. So like satellites in space, and there's more and more all the time, will be bombarded with various sorts of radiation, heavy ions, cosmic rays. Ionizing radiation, though, is there, and it's there in fairly low dose rates. And so, but the satellite needs to live for 10, 20, 30 years, and all the while maybe gathering a few tens or so of kilorads of total dose. Sounds like not much of a problem, but in fact, if there's a low dose rate response that's different than what you can test easily, in a lab in a reasonable time frame, then that's a really big problem with a lot of dollars at risk putting a satellite up there. That's a big undertaking, obviously expensive. So that's
Absolutely.
why there's even more interest in the field, I think, and that's why it's continued to be relevant, even today.
Yeah, the concept of rad hard chips is always in electronics has always fascinated me,
Yeah,
and it's such a complex topic. Like you said, you can't stick something in a chamber for 20 years and see how it performs. You have to
right.
find a way to accelerate that testing. So after grad school, what was your first role? Was it semiconductors?
Actually, after grad school, I spent 1 week at Sematech, and that's all. So then I moved on from Sematech to VTC, which was in Minnesota, is in Minnesota, or was in Minnesota, in back where I went to school, and where I met my wife, and close back to family. So I was excited to move back and take a job at VTC Incorporated, which was a maker of hard disk drive chips, analog mixed signal chips, and had its own fab, developed technology, bipolar processes, complementary by CMOS, very focused on the target market and the applications. So I was excited by that opportunity, the chance to come in and do real things right away, and also the chance to be involved in not just the fab but the product side and all of that. So it was a great place to come and work.
It's time for a quick break, but we'll be right back. I wanted to take a quick moment from our podcast to personally invite you to join Industry Tech Days 2022. It's a free 5-day digital conference and trade show designed for engineers, brought to you by All About Circuits. Registration, it's open today, and the event runs from September 19th through the 23rd. Go sign up now at allaboutsircuits.com and look for the Industry Tech Days link up near the top of the page. While you go sign up, we'll get back to our podcast with Steve Kozier, CTO of SkyWater Technology. So Steve, you've been in the semiconductor space for a while. What was it like in the 90s? Was it thriving? Did it feel like it was maybe moving overseas?
Right. It was just at the start of the fabless foundry model back then, and TSMC was there, but not really a strong player yet. And feature sizes back in that era, you might be talking about half a micron, 0.35 micron. You might be talking about moving from 6-inch wafers to 8-inch wafers at that time frame. And there were still a lot of fabs around, and they tended to be smaller fabs. They tended to have larger feature sizes, but it also, since it wasn't so incredibly expensive to make a fab, there were more of them, and more companies had them, and there were more IDMs, integrated device manufacturers, such as VTC was, that could still kind of keep up with the progression of the feature sizes at that time. But it was already starting to be a little bit more of a diversification to fabless and foundry model, just because the costs were already getting pretty high.
Can you walk us through what is a foundryless model?
Oh yeah, so an IDM, at least in this context, will have its integrated device manufacturer. So the design and product is in the same company, often in the same building, perhaps, as the manufacturing, the factory, the wafer fab, the test, maybe even packaging. So it's all integrated, all in one place. The fabless piece will be the design piece, the layout, all the sales and marketing of the chips, basically the business, and then the manufacturing, the foundry is purchased as a service, and somewhat as a partnership in that model. So it's a breakup of an IDM into two separate entities, and the advantages, of course, are the design people can focus on their designs and where they add value. The foundries can diversify their inputs from many different customers and not just rely on the local in-house design group to generate wafers for them to run. So it makes a lot of sense in that case.
But VTC was operating as an IDM.
VTC was operating as an IDM, operated as an IDM all the way up until 2000, when even VTC succumbed to that pressure and split apart into two. There was a piece that got sold to Lucent Technologies in 2000, and the piece that stayed behind the fab became Polar Fab, and I stayed with the Polar Fab.
In the fabless architecture, what do people miss on either the design side or the manufacturing side? What is lost in that translation that maybe people should think about if they're in those spaces?
Well, the thing is that, if you think back to those times, then the designers would know the people in the fab. They would talk to each other. We'd see each other in the break room. We would ask how it's going, and yeah, I need a better performance in this transistor, or what happened to that lot, and you go talk about it. So there's much more of a communication going on there, and also a chance to optimize things to give some advantage. It's like, for example, in the case of disk drive chips, the feature sizes are not so small, so it's potentially anyone could make them, or there's a larger number of folks that could make them, but it's not just that. It's that plus other things, like maybe the beta need to be high, or the base resistance needs to be really low, or you need a capacitor in there that's very linear, or kind of these application-driven customizations to processes is what makes it work. And it's easy to do that in an IDM, easier anyway, and less easy to do in a fabless foundry model, especially when the foundry's overseas, and especially when that foundry overseas wants to run the same thing all the time, not hear about new things that you might have up your sleeve.
Do you have any advice for folks in those situations to make their designs better or improve their fab processes to better serve their designers, customers?
So I think as a designer, you want to obey the rules of the process, right? There's always design rules that are there. What a lot of designers don't get, though, is that, yes, there's design rules, but there's also best practices, call them manufacturing rules. Like, don't run a long, skinny line down the middle of the chip. Just don't do it. If there's room to put two vias, put two vias. Don't just rely on one. You can make your life a lot easier if you just do things that are kind of common sense. Call it common sense to someone that's dealing with wafers, not so common sense maybe to CAD tools. And so if you have that experience kind of dealing with the physical reality of processing, what's easier to do and what's not easy to do. So to some extent, you can put that into code for manufacturing rules, but there's still some art to it.
Can you tell me about your transition from Polar Fab to SkyWater?
Polar Fab ran as a pure play foundry from 2000 to 2005, eventually sold the company to a Japanese company, Sanken Electric. Then Polar Fab became Polar Semiconductor. Polar Semiconductor is still here today. It's still in Bloomington, Minnesota, still doing very well. But I was with Polar Semiconductor from 2005 to 2017. And during that time, we went away from being a pure play foundry and into a captive fab for the Sanken Group. And that included Sanken itself, also Allegro Microsystems, which is also owned by Sanken. So based on that partnership and the stability and funding that the Sanken Group brought, we're able to grow the factory quite a bit, move entirely from 6 to 8 inch wafers, and really focus the business on automotive and high voltage and BCD processes that have become super important today and keep growing in use throughout the world, and all the vehicles and all the industrial applications of very high voltage technologies and circuits that can deal with that. So the Sanken acquisition, the Polar sale to Sanken, and then association with Allegro has been nothing but great for Polar Semiconductor. I left Polar Semiconductor in 2017, but then I went to be president of a startup company in town here locally, making nanoparticle instrumentation measurements. It's a great company, very advanced instruments, selling to the semiconductor business. So, and because you're trying to measure particles down to 2 nanometers and things like CMP slurries, ultra pure water, isopropyl alcohol. These kind of things are super important as you scale down to smaller node sizes. But I was aware of SkyWater and what SkyWater was doing. I loved the SkyWater mission, and I loved all of the exciting things that was happening at SkyWater, and also really missed the semiconductor business and how fast it is and how exciting it is and how quickly semiconductor solutions can change the world because they get out there and can make a big difference right away. So I was really happy to join SkyWater in 2021. I've been here about a year and a half now. It's a great place. I love it here. So that was kind of my journey to get to SkyWater.
I understand that SkyWater has US-based fabs. Can you talk about the state of manufacturing now in the 2020s, especially with the CHIPS Act and some of the other things that are happening globally?
Yeah, so SkyWater is the only US-owned pure play foundry. So that's kind of amazing. SkyWater is not a large company. We're getting bigger, but we're not big. But we're the only US-owned pure play foundry. And that just is reflective of just the harsh economics of the situation, and also just the fact of where the business has gone over the last several decades. The cost to build a new wafer fab at a leading edge node today, like let's say you want to build a 3 nanometer factory that's actually going to be profitable, or at least get your money back over the next several years, you're talking about $10 billion, right? That's billion with a B. The Asian countries have known this is important and wanted to invest in it, and have been doing so for decades, really. So, now U.S. with the CHIPS Act is kind of recognizing that that's what it takes, recognizing that even though the right move for your P&L might be to say, this manufacturing stuff is hard and it's expensive, and gee, these guys over there will do it and they won't charge us much money. And that seems like a really good idea. And of course, it does make a lot of sense financially, but the reason they're not charging us much money for the wafers is because the government's subsidizing it heavily. And it all works great right up until it doesn't, right? Right up until, you can't get the chips you want, or right up until there's some geopolitical reason why you may not get all the wafers that you wish for. So, that's sort of where the CHIPS Act comes in, and I'm super excited that that's happened now. SkyWater, of course, being U.S.-owned pure play foundry, expects to participate in that, as do many others. But it's a great thing for the country.
So what is SkyWater's mission? What gets you excited and what gets people excited about working with SkyWater?
Yeah, SkyWater's mission, SkyWater's vision is to improve the world by revolutionizing technology realization. And so what that means is that the world of semiconductors, of wafer processing, it's such a flexible and powerful way to bring solutions to the world. One way to look at it is you want smaller and smaller features for faster and faster digital chips. That's important. That's called Moore's Law. That's chasing Moore's Law. But there's another way to look at it. Sometimes it's called more than more. In fact, this podcast has more in it, right?
Moore's Lobby, yeah.
So it's more than more, meaning that, okay, but at any particular node, technology node, there's all sorts of other things that silicon can do to improve the world, right? There's power management efficiencies that can be had. There's superconducting chips that can be built. There's silicon photonics chips that can, revolutionize that space. There's all sorts of MEMS, micro electromechanical system chips. There's biomems. There's microfluidic chips. There's all sorts of things that you can do with the same equipment set and a little ingenuity and some co-creation with our customers where they want to go do something new that doesn't exist but is potentially revolutionary. How do they get access to that capability? It's not easy to do. It's often beyond the capability of any kind of lab. And usually, a volume semiconductor fab doesn't want to entertain such business because it's a diversion. So there's this big gap in the middle, but that's right where SkyWater plays. That's technology as a service. That's what we call it, where we have from lab to fab, we can take stuff that is demonstrated in a lab, or maybe there's a proof of concept, and bring it into volume manufacturing, all in the same building, all in the same factory. It's a very powerful thing for creating the next things, for creating new things that don't exist and bringing it into the market quickly.
Yeah, I was gonna say, being the only pure play fab in the US means either the company's really stubborn, which is clearly not the case, or there's a unique angle or approach that works, and technology as a service makes a ton of sense for that. How does that work, and how do you make that work with your customers? What does that look like?
Yeah, so there's a few things that make technology as a service work. One is that first and foremost, this is a volume production facility. We run volume. We run for the automotive industry all sorts of highly stable and world class manufacturing exists in the facility, and it's hard to combine that with new things, which is what Advanced Technology Services (ATS) does. But there's also a strong benefit for the ATS projects because when you have such a solid base, high quality controls, and so on, it makes it so much easier to do new things because the new thing is going to be a perturbation, let's say, off something that exists, and that which exists is stable. And so it's just much quicker and easier to get to a stable solution. And because it was all done in a production environment, it can go to production quickly. And so this is what SkyWater does differently than, let's say, Albany Nanotech Center or IMEC in Belgium or CEA Leti in France or Fraunhofer in Germany. These are places that do lots of very great and interesting research projects. But these places are not production facilities. If you want to run production, that's great. They'll give you a license and say, go find somebody to make it for you. But with SkyWater, it's all in one place. So we really thought there was a big need for that model, and the company was founded on that. Our CEO Tom Sonderman has kind of pioneered this model, and we're executing it.
Speaking of executing on a model, it's time for another quick break, but we'll be right back. "15 minutes ago, I invited you to go sign up for Industry Tech Days 2022, the free digital conference and trade show. If you haven't signed up yet, I get it, maybe you were driving or something, but now it's time to go sign up. This event has live sessions from some of your favorite folks like DigiKey, Mouser, Infineon, Rome, Eaton, Rodian, Schwartz, and more, and each registrant is entered to win a grand prize and a bunch of swag. I'll tell you more about the prizes and the swag in a bit, but I am once again inviting you to come join us. Sign up for Industry Tech Days 2022 at allaboutcircus.com. And we're back with Steve Kozer, CTO of SkyWater Technologies. Steve, I'm curious, with the abundance of fab options out there, why do people choose SkyWater?
Right. So if you're a design house, let's say you're making a design and you can use a standard CMOS process and it's available from lots of places, you would have choices. You might come to SkyWater, you might not. The reason you might come to SkyWater is if you needed a trusted foundry, if you were trying to sell to the U.S. government, if you were particularly concerned about IP protection. SkyWater being a U.S.-owned entity, we're very focused on IP protection and obeying all the laws, and everyone's IP is kept strictly theirs. Not so much in the Far East. Okay, so those would be reasons to come to SkyWater. But if what you're trying to do is, I have an idea. I need some CMOS, let's say, but I also need to add a structure here, a feature there. needs to do something special, something different, that's when SkyWater is really the place you want to come and talk. Because so when you're trying to figure out, okay, I have this great idea, and I can draw a picture of it. I can draw a cross section. I need the wires to go like this. I need an etch thing that goes in there. I need this material here. I don't know how to do it. Who can do it for me? That's the kind of customer that comes to us all the time. And then we engage and scope it out and quote it. And, oftentimes these become, very successful engagements.
What is the most wild or off the wall chip or design or architecture you've been asked to make? Obviously, that you can talk about.
So a good one there to talk about would be our partnership with Rockley Photonics. So Rockley Photonics is building a kind of a lab on a wrist chip. So this is something that is going to combine silicon. It's a silicon photonics chip, but it's a wearable. So it goes on your wrist, and it can monitor into your skin and into your bloodstream, and do a lot more than just find your heartbeat. It can find your glucose level. It can find your level of hydration. It can do all sorts of really interesting things that today require that you be in a hospital room with some tubes hooked up and stuff to you to know. But with this, you can just have it on your wrist and know all the time. And so to make that happen, it takes a lot of special processing. It takes photonics, silicon photonics integration, which we can do and do for many customers. But it's not just that; it's that, and then the wafers need to go from Minnesota, where a lot of the silicon photonic stuff happens, goes to our Florida facility, which is a advanced packaging hybrid integration facility for some gold deposition and etching. Gold is important in this application. Gold does not belong in a CMOS fab, so we can take it to Florida for that processing, and then it gets combined with other wafers for the lasers that excite the waveguides and also penetrate the skin and measure the reflectance back. So this is a highly complex, highly integrated chip, which is going to be a revolutionary advance for the market that is really hard to accomplish without doing a lot of special things. That's a perfect kind of example for what can an ATS model bring? What kind of innovation can you bring with that?
That sounds like an incredibly useful and valuable technology to be able to throw in a smartwatch and monitor health. And that's like incredible.
It is. It's crazy. It's Star Trek or something.
Yeah, it really
But it's
is.
happening.
Yeah.
Yeah.
So looking back at the last 20 or 30 years of semiconductors and fabs and manufacturing, what has surprised you and what has been constant that's been something you think may last into the future?
The thing is that semiconductors, they're pervasive in our world, in our life, and they're getting even more so. So the continued growth of semiconductor content in just everything in the world, it's follows a power law. It keeps growing, and it keeps growing and growing and growing, such that semiconductor business could exceed $1 trillion in just a few years. And that's such a big number. It's a large percentage of the world's GDP. And you think about, okay, where is all that going to come from, and how is it all going to get designed, and how are you going to deal with all of those semiconductors, all that content? Where will they come from? One trend that's happened, right, is the fabless foundry model. This is necessary to keep up with the Moore's law and the fact that it costs $10 billion to build a brand new leading edge fab. That's one thing. But it's also semiconductors became relevant or important for all of us recently. And the thing that got people's attention was, why can't I get a new car? And why do the cars cost so much? And where are all the used cars? And so people understand when there's something with the automotive industry, it kind of resonates with Americans, I would say. And then COVID is there, and the explosion in all the chips, and so all the supply chain issues coupled with China and geopolitical tension and Taiwan, where all these chips get made. kind of a perfect storm. Of course, it's what led to the CHIPS Act. But if you look at all of this on a log scale versus time for decades, the industry's been growing at a trend that's been going up and to the right for a long, long time. And there's nothing, it's maybe accelerating a little more now, but not crazy more. It's not like you couldn't have predicted some of this might happen. Just all these things came together at once, maybe brought on by COVID and other issues that now all of a sudden it's in everyone's discussion. So that's certainly a new thing. I mean, if you would have asked me a few years ago, would politicians ever want to show up at wafer fabs and get their picture taken? I'd have thought you were nuts, But now they come from everywhere and they want to be associated with it because they've appreciated how important it is and they understand it's a national issue. So it's great. I'm happy for it. I want more, but that's certainly a big difference. And getting back to SkyWater's vision is to improve the world by revolutionizing technology realization. One of the things we're really proud of and excited about in this vision is the fact that we've open sourced our process technology. So what that means is it's really quite revolutionary. What it means is that partnering with Google, Google has a vision that software engineers should be able to design chips, and it should be just as easy as writing code. And their observation is they look at the same exponential growth and say, we need all this silicon, we need all these chips, they need to be custom. Who's going to design them all? Where am I going to get them? How much am I going to spend on all these EDA licenses? Just how is this going to work? It doesn't work. And so part of the answer is, well, make it look more like software. So what you can do today, right now, anyone can go type into their browser, type in Sky 130, SKY 130, and you will go to GitHub and you will be able to click and download all the design tools you need to design a chip in SkyWater's process. And you can submit it to a free shuttle that's run by Google and administered by eFabless, and you can get your chip built and you can get your chips delivered to you for free. So think about that. That's totally revolutionary. I mean, who gets to design a chip today? You got to work at a chip design company. That company has to have all the licenses they need. They have to have executed all the NDAs. You have to have the budget to have bought all those tools. You have to have a network administrator install it all for you. You have to have a foundry arrangement. You have to agree on pricing. You got to get somebody to package it for you. I mean, there's like so many things that have to be there for you to even start that it's essentially, all but the very few are going to ever attempt it. But what if it was just all free and it was all there right now? And it is there right now. You can go do it right now. And it's just awesome. And we've seen a huge uptake, exponential growth in the number of designs that are submitted. A lot of these designs are done by first-time designers, by software engineers. They just learn to run the tools, they run the code, and out comes the logic. You can synthesize RISC cores. You can customize it to your application, and it's just revolutionary. And the keys that make it so are that it's free. It's free to everyone. It's free to everyone in the world. And you can learn it on your own. You can watch YouTube videos. It's being picked up by all sorts of universities within the country, around the world, really. It's even being taught now in some junior college kind of trade schools, even high school level. There's nothing stopping you from designing a chip and changing the world with it. So that's something that I'm super excited about and is absolutely different than what's going on traditionally, because the traditional way of fabless foundry is that you're going to move to the next node. It's a huge investment to get there, and you have to protect that investment with fanatical fervor so that you can preserve your advantage long enough to get your money back and not lose your shirt, right? That's the way that game is played. But when you step back and say, well, we're not chasing Moore's law, we're making chips at a much different line width. It's more about we have this capability let's open it up and let's find ways to use this, capability to innovate in all sorts of areas. And you never know where the next great idea is going to come from. And you can't have such a penalty for failing, right? There's a huge pressure to get it right when there's all that money at stake. So of course, you're going to heavily watch and scrutinize and pay attention to every little thing and make sure it follows the process, because the cost of failure is so high. But what if it didn't cost anything and the cost of failure was nothing, right?
Yeah.
I mean, there's no consequence if your, JavaScript code doesn't compile right. You just fix it and go again, right? So why can't chip design be like that? And it can, using open source tools. So I'm really excited about open source.
Yeah. I just want to reemphasize that anyone out there can create their own chip through an open source tool chain and get it fabbed with Google on one of their multi-project wafers. And this is literally a multi-million-dollar sort of capability that you get for free through this collaboration that you have with Google. It's incredible.
That's right. It's amazing. It's remarkable.
If someone wants to go do that, I'm familiar with, a friend of mine, Matthew Venn, does the Zero to ASIC course, and they walk through the whole process from start to finish. Are there any other learning resources or places people should go if they want to learn more about that, maybe fab their own chip?
Right. So you mentioned Matt Venn's courses. Those are really great, step by step. I think there's a guy in India, actually, Kunal Ghosh, that's running courses on the same kind of thing. There's probably other folks on YouTube that have put their courses up for how to use the tools. And, of course, there's documentation online, design manuals and all that sort of thing. So there's quite a lot of info. You can pick it up on your own and pretty quickly, too.
It's time for another quick break. We'll be right back with Steve Kozer, CTO of SkyWater Technology. Okay, I told you I'd tell you more about the prizes for Industry Tech Days. We're giving away custom soldering mats, t-shirts, and one grand prize winner will win a fully loaded InstaLab kit with test gear, tools, components, and more. Industry Tech Days 2022 kicks off September 19th, and it's free, and I'll be there hosting the keynotes. So if you've made it this far into the podcast, I promise you this event is right up your alley. Go sign up at allaboutscircuits.com. And we are back. Steve, I hear you're doing some interesting work in silicon photonics. From a fab perspective, can you tell me what makes that technology tick?
So a CMOS fab is pretty well set up already to do silicon photonics kind of work. There's just a few special things that you need for the photonics and a few optimizations that need to be done differently. So silicon photonics is all about waveguides and optical mixers. And so you get a lot of shapes that are, circular, right, to make the light take a little longer, and then combine it with other light. And then the interference, is interpretable. And of course, there's detectors, photoreceptors, photodiodes, lasers. There could be waveguides coming in, whatever the case may be. So in terms of processing those wafers, it's really important to make waveguides that are very precise, very smooth. The edges have to be very smooth, because if they're not, they can be lossy, and that's not good for the system. So anyway, SkyWater has many silicon photonics customers and projects that we are doing, and have a lot of expertise in that area. We mentioned Rockley Photonics; that's one of them. There's others.
You mentioned your Florida facility and you brought it down there for gold. Can you tell me what you're doing at your Florida facility and maybe a little bit about the heterogeneous integration? Yeah,
right. Florida. So SkyWater Florida is in Orlando area in Kissimmee, and it's the former Bridge facility, BRIDG. So it's a Osceola County funded center. And SkyWater took it over a little over a year ago. And so we're the operators of the facility. And this facility is all about hybrid integration. So what it means is think of wafer to wafer bonding. You got one wafer, you're going to put it on another wafer and smash them together. So So this is really important for things such as imaging, where the imaging, sensor is here and it sits right on top. All the pixels sit right on top of the electronics to drive it. And also 3D integration generally. This is the trend in the industry of, instead of going out and trying to push features back in by smaller and smaller feature size, how about we go up instead and get the performance that way? So Florida is all about hybrid integration. So hybrid integration is just two dissimilar things brought together. In this case, two wafers that may have come from very different factories.
Yeah, we alluded to that a little bit in a previous episode. We were talking with someone at AMD about chiplets and how they made the 3D silicon devices work, and it was fascinating.
So a chiplet approach is to singulate the wafer into die and then place them on top of a common die, as opposed to a wafer on top of a wafer and then putting them together as one. Both are important.
That's a good distinction. Thank you. And then recently, SkyWater and NanoDX announced the first commercially ready nano biosensor to yield a protein response. Can you tell me about this collaboration and decode that phrase for me?
NanoDX is a startup company. They license technology from IBM, and this technology is basically a nanowire, kind of like a FinFET, but not quite. When the wire is exposed to fluid of different pH, then the threshold voltage or the resistance of the wire will respond to that. So the way you use that in a product is that you can take blood or saliva, and if there's something different about your fluid, then by combining it with certain antigens, anyway, the nanowire will respond to changes in pH. But the way you trace that back to what's actually going on in your blood, like for example, when you have traumatic brain injury, a concussion, there is a change in your blood that is there, but you couldn't detect you have a concussion without going in to get an MRI or some scan. But wouldn't it be great if you could figure out just by taking a blood sample? Well, you can if you can take the blood and combine it with the right fluids. So depending on what you're looking for, the target biomarkers can be functionalized, and so the kind of the secret sauce is what do you take you get your blood, what do you combine it with, you put them together, and then based on what they bind to and how it attacks, then the pH can shift, and that shift can be detected in minutes. And so then, depending on what you're looking for, you can find out if the condition is there or not.
Huh. Interesting.
So what would take days, perhaps, in a trip to the hospital, can be done in minutes with the right kind of system. So it requires that you build the wafer correctly and in such a way that it can be used in the application as intended. So that's where the co-creation of these solutions comes in with the customers. That's why it's so important. NanoDX is trying to do something new, something different, something that will benefit the world. But in order to do that, the silicon needs to look a very certain way, a very specific way, a very different way than what everyone else in the world wants, right? So that's kind of the essence of what ATS means. That's the technology as a service model. We can partner and make this technology, and we can take it into manufacturing.
Yeah, there's no library where you can just drop in that architecture. That's
no, sure. Right. It's kind of the opposite of that, actually. It's just it's new to this world. So
yeah,
that's the exciting thing for sure.
Another phrase that caught my attention was adaptive patterning. Can you tell me more about that?
Right. So in Florida, we have licensed the Deca technology, and what Deca technology is, it's a wafer level fan out packaging technology. And what that means is that you can put your chips down that you want to interconnect on one plane and then connect them all together. But the thing that's special about it is that the adaptive patterning takes a picture of each and every example of it and then identifies where each and every pad actually physically is this particular time. and then goes and routes to those exact locations. So one of the problems with, getting tight pitch interconnect in this kind of system is that because there's some slop in how precisely these things are really going to be placed, you have to account for that. And so you end up having really, really big landing pads, which of course destroys the pitch. But if you just each and every time, the system takes a look and knows exactly where to go and then writes exactly there, then you can have much tighter pitch. So you can actually get best in class, world class pitch out of this solution. So that's what adaptive patterning is.
I imagine in this space, you're always looking for new capabilities and new and unique ways of approaching things. I understand you're working on a fab with Purdue. Can you tell me more about that collaboration?
Right. Yeah. Collaboration with Purdue. It's very exciting. So we announced that we're going to build a fab on the campus of Purdue. So this will be a 300 millimeter fab, and it'll be, we like to call it an innovation center to distinguish it from a fab, which is just going to run production. So this will implement, our technology as a service model. We have call from many customers to expand capacity for sure, but also the 300 millimeter wafer is, necessary, especially to go to smaller features than you can get to on 200 millimeter wafers. It's a result of basically a new way of doing fabs or innovation centers. So it's heavily relying on public-private partnerships. So state of Indiana, federal funds through CHIPS Act, our customers, our partners, and of course our money all need to come together to make it a reality. So this is the sort of facility where we're going to be running production, but also doing innovation, just like we do in Minnesota, just like we do in Florida. And being on the campus of Purdue with semiconductor degrees program that they've announced and all that pipeline, it'll be just a big thing. And it's more than just a fab. It's a ecosystem. For example, fab tool vendors may want to lease space in the facility, or the people that contribute to the ecosystem of making semiconductor wafers can all participate. And SkyWater has a generally more open view to sharing data. And, this is in line really with what the NSTC is all about, National Semiconductor Technology Center's concept is all about, that's in part of the CHIPS and Science Act. So we think that this approach, the SkyWater business model, the fab at Purdue, they're all really well aligned with that, with where the country's going. So
yeah, you're almost building your own pipeline of future engineers and future technology advancements in the space.
Exactly. Everyone talks about, great, we're going to build fabs, but where are all the people going to come from, and how do we hire them all? SkyWater's no exception. We have so many openings. We have lots of openings. Please apply, and check out our job openings. But it's a big problem, and looking forward to getting wafer fabrication, semiconductors back into the curriculum, getting more students exposed to it, and then more of them will look at this and say, yeah, that's a pretty good career. There's something there for me. And I think the signal that the government sent by funding the CHIPS Act sends a strong message to everyone thinking about, okay, what do I do? Do I go this way? Do I go that way with my major? That there's a future for semiconductor manufacturing in the U.S., and so they'll be more inclined to go that way. That's a big deal. It takes years, but that's the right first step for sure. And of course, partnering with Purdue is a natural because of their semiconductor degrees program that they're working on rolling out, and that'll be a pipeline to feed the talent.
Did I hear you say a larger wafer enables a smaller node?
Well, yeah. There's no particular reason that would need to be the case, but it just is the way it went. And again, it goes back to Moore's law scaling. So the fact is that the tool makers, the most advanced tools are made for the most advanced nodes, and the most advanced nodes exist on the largest wafers.
Okay.
And it's just a matter of economics, to process a 300 millimeter wafer doesn't cost really that much more than processing a smaller wafer. So you just get lower overall cost per die on a 300 millimeter wafer. So to get below 65, 45 nanometers kind of features, you're really looking at 300 millimeter wafers.
It's more the technology pipeline than a physics concern.
Yeah, no, it's really it's an economics. The industry for a time flirted with going to even bigger wafers beyond 300 millimeter, 450 millimeter. But yeah, there was a revolt against that. So we're staying at 300.
It's a happy place, I guess. So we're running out of time, but at the end of all these episodes, we like to do a quick lightning round, some of the fun, quick answer type questions. My first one for you is, have you ever seen semiconductors in pop culture, be it fiction, movies, TV shows, and have they gotten it right or wrong?
I can never remember ever seeing it gotten right. But it's kind of like Star Trek. They like to throw phrases around like quantum and quantum drive, and it was Back to the Future, right, with the flux capacitor. So anyone who's studied engineering knows that these are kind of crazy words to string together. So
the quantum flux core is overheating. Yeah,
exactly.
If you could teach any electrical engineering class, what would it be and why?
Right, I would teach analog circuit design. Analog design, there's an art to it. It touches high level system thinking all the way down to transistor level, behavior, and analog design is just a beautiful thing. So I would teach analog circuit design.
Wonderful. And then, have you ever put anything that maybe wasn't designed to be in a radiation chamber in a radiation chamber?
Well, I used to radiate our chips back at Arizona in the radiation facility there, but I think I missed an opportunity by not irradiating things I shouldn't have. So I can't say I have, no.
So if you had access to a chamber and you could put something in there, is there anything you would?
Maybe there's a way to irradiate some sort of footwear or something and make mark them up that way, especially radiated.
Yeah. 5G proof sandals and sell them to the tinfoil hat people.
Right. Maybe somehow those those bracelets that had the little magnet in it, that's supposed to give you balance. Maybe for an upcharge that could be radiated also, and then
there you go.
Then they could be even special, maybe even more special.
You could do that in your garage. Just get a little chamber and a license.
Yeah.
All right. Well, this has been a blast. We're out of time. Thank you so much.
Yeah. Thanks, Daniel. It's been a pure pleasure.
That was Steve Kozer, CTO of SkyWater Technology. Please make sure you are subscribed to Moore's Lobby in your favorite podcast system, including YouTube. And hey, I'll hook some folks up with a Moore's Lobby mug. I use mine all the time. All you have to do is hop on the Moore's Lobby Facebook or LinkedIn pages and share this episode's post. Bonus points if you leave a comment telling me the correct way to pronounce solder at me. I feel like I always say it wrong. And hey, you could win a sweet soldering mat as part of Industry Tech Days 2022. If you miss any of it, you can also catch it on demand. I'll be there. We'll learn a bunch. It'll be a party. Thanks for joining me today in the lobby. I'm Daniel Bogdanoff, and I'll see you at Industry Tech Days 2022. Hey Google, how do you pronounce solder?
According to English Stack Exchange, depends on if you are British or American. The British say solder, Americans say solder.
And then in parentheses it says, for some reason.